Open the picture scroll of history, bronze chariots and horses, Simu we big square tripod. Looking forward to today, Tiangong Space Station, Hong Kong Zhuhai Macau Bridge. Take another look at the buildings we live in, the means of transportation we travel, and even the mobile phones we hold in our hands. Their existence is inseparable from metal materials. In this lesson, we will understand the mechanical properties of metals. The mechanical properties of metal materials refer to the ability of resistance to deformation and fracture under various external loads, tension, compression, bending, torsion, impact, alternating stress, etc. The common mechanical properties of metals are strength, plasticity, hardness, impact toughness and fatigue limit. The strength and plasticity of metal materials can be determined by tensile test. What is a tensile test? Tensile test refers to the axial tension of the sample under the action of static tensile force, while continuously measuring the force and corresponding elongation until it is broken. During the tensile test, the tensile testing machine can automatically draw the relationship between the load in the reaction tensile process and the elongation of the sample. This relationship is known as a stretch curve. The shape of tensile curve varies with the properties of materials. Now we see the tensile curve of annealed low-carbon steel. The ordinate in the figure represents the force. The unit is Newton. The abscissa represents the absolute elongation delta L. The unit is millimeter. In the stretch curve, OE is a straight line. When the tensile force does not exceed Fe, the tensile force is proportional to the elastic deformation of the sample. When the force reaches Fs, the sample continues to elongate even if the tensile force does not increase. At this time, you can clearly see that there is a platform section on the tensile curve, namely S-section. The material has lost the ability to resist deformation. We call this phenomenon yield. In the SB section of the tensile curve, the load continues to increase and the sample extends uniformly along the axis. We call this stage the uniform plastic deformation. At the highest point of the curve, point B, when the load increases to the maximum value Fb, the local area of the sample will decrease, while the elongation will continue to increase, forming a necking phenomenon. With the continuous reduction of the section at the necking point and the continuous decline of the bearing capacity, the sample breaks when it reaches point K, and the whole test is over. From the static tensile test of low-carbon steel, we can know that during the tensile test, OE section is the elastic deformation stage, S section is the yield stage, SB section is the plastic deformation stage, and BK section is the fracture stage. As we all know, excessive plastic deformation is not allowed when the ship structure or hull parts are working. Therefore, yield strength is one of the important mechanical indexes in engineering technology. Yield strength refers to the stress point at which plastic deformation occurs, but the stress does not increase during the test when the metal material presents the yield phenomenon. The S section we just talked about, which is divided into upper yield strength Re and lower yield strength Rel. Tensile strength refers to the maximum stress that the material can bear before fracture, which is the point B in the curve just now, is also known as strength limit. Tensile strength is the main index of mechanical engineering design and material selection. Especially for brittle materials, tensile strength is also the breaking strength of materials. Metal plasticity refers to the ability of metal materials to produce plastic deformation without causing damage under static load. We use elongation after fracture and reduction of area to express. What is elongation after fracture? It refers to the ratio of the ground elongation of the gauge length to the original gauge length after the sample is broken. The reduction of area refers to the ratio of the reduced cross-sectional area at the tensile fracture of the sample to the original cross-sectional area. The larger these two values, the better the plasticity of the material. Good plasticity is of great significance to the processing and use of metal materials. Next, let's learn about hardness. Hardness is an index to measure the hardness and softness of metal materials. It is the ability of metal materials to resist local surface deformation, especially plastic deformation, indentation and scratch under static load and force. We mainly introduce Brinell hardness and Rockwell hardness. First, the advantage of Brinell hardness is that it can better reflect the average hardness of materials, and the data is relatively stable. Its disadvantage is that it has large indentation when measuring, and is not suitable for measuring finished products or thin parts. On the contrary, Rockwell hardness measurement is fast and simple with small indentation. It can measure finished products and parts. Its disadvantage is that because its indentation is small and its accuracy is not high, it needs to be measured for many times to calculate its average value. Impact toughness. The ability of metal materials to resist failure under impact load is called toughness. Many materials have to bear the impact load when working. The effect of impact load on material damage is much greater than that of static load. If we only use the strength index under static load for calculation and design, we cannot guarantee the safety of parts when they work. The impact toughness of materials is usually measured by a pendulum impact test. The impact toughness of materials is usually measured by a pendulum impact test. Now you can see the sample of a pendulum impact test, which is a rectangle with a length of 55 mm and a width and height of 10 mm respectively. And there is a slot in the middle of the sample. So what is the purpose of the slot? During the test, the sample will break at the notch and the energy will be absorbed by the weakened part. At this time, we observe the sensitivity of the material to defects such as stress concentration. During the test, place the standard sample on the support of the testing machine, lift the pendulum with mass of m to a certain height h1, and then release the pendulum to break the sample. The pendulum moves to the position of height h2 by inertia. The potential energy loss of the pendulum is the energy required to break the sample, that is, the work consumed by the deformation and fracture of the sample. This work is called impact absorption energy K. K equals mg, h1 h2. After the test, we come to a conclusion that the greater the impact absorbed energy K, the greater the toughness of the material and the more it can withstand the larger impact load. Now let's look at metal fatigue. Speaking of this, some students will certainly have questions. Will metals also be tired? In fact, many parts work under alternating stress or repeated stress for a period of time. When the working stress is far less than the tensile strength or even the yield strength, it will break suddenly without any sign, which is very dangerous. We call this metal fatigue. We all know that when people are tired, we can have a rest and sleep. So is metal okay? We can definitely tell you that we can improve the fatigue limit of metals in the following 3 ways. First, the shape and size of parts should be reasonable in design. Try to avoid sharp corners, notches and abrupt changes in section, because these places are easy to cause stress concentration and fatigue cracks. Second, we can reduce the surface roughness of parts and improve the surface processing quality. Reduce the presence of surface fatigue sources. Finally, when the parts have been machined, we can adopt surface strengthening treatment. For example, carburizing, nitriding and surface quenching can effectively improve the fatigue of metals. Okay, this lesson is about the mechanical properties of metals. Thank you for watching. Goodbye.